Hello, welcome to day 8 of Leetcode 75. We're doing reorder routes to make all paths lead to city 0, which is problem 1466. So there are n cities that are numbered from 0 to n-1, and there are n-1 roads such that there's only one way to travel between two different cities. So this network is going to form a tree or a acyclic graph. A directed acyclic graph, so a DAG. So last year, the Ministry of Transport decided to orient the roads in one direction because they're too narrow. So the roads are represented by connections, where the connections of I is equal to A sub I, B sub I, which represents a road from the cities A sub I to B sub I. So this year that there's a big event in the capital, which is city 0, and there are many people that want to travel to the city. So our task is consisting of orienting some of the roads such that each city can visit the city 0, and with return minimum number of edges guaranteed or change, and it's guaranteed that each city can reach city 0 after some reorder. So this is an example here where we have there's 6 nodes here and there's 5 edges, and we want to point all of the roads so that it points to 0. So essentially everything that is 0 that is pointing to something, or like a node, anything that is within nodes hierarchy needs to be pointing towards 0 essentially. So we have to change the direction of the edges so that each node can reach the capital 0. And we can see that anything in the second position is the direction that the node is going towards. And we can see the same case for example 2 here. This is where we just everything that's kind of within 0's hierarchy again needs to be flipped so that it points towards the direction of 0. And again, if there's if there's 2 nodes, 1 is pointing to 0 and 2 is pointing to 0, there's no need to have any nodes changed because they're already all pointing towards the capital. So there's no edges that needs to be changed at all. So the way that we can solve this problem is by using a depth first search. So we basically go through this entire branch right here, and we check to see okay, are all of the nodes under here pointing towards 0? If not, flip it. If not, flip it. Keep going further and go down this branch as well. So there's 2 branches to consider, and we just go down every single branch and then flip their order. Technically you can do a breadth first search here too, but I think it would be faster to do a depth first search here, since we can just do them kind of all in one go. And also I believe depth first search will be excuse me. DFS will take less space, but I think it'll be a bit slower than BFS if I remember correctly. Actually, wait, they can be slower, since especially when the graph has a large width or the target node is close to the root. So it explores far from the root and before backtracking, and they're usually the same complexity, but DFS can be slower than BFS, but it's more space efficient. So the way we can solve this problem is by considering something called an adjacency list, which is essentially just mapping out the relationships between each node, and we need to be able to visualize what does each node's edges or connections look like, and how their direct connections, and we need to be able to explore their relationship further. In this case, it just means that we need to see the direction that the direction of each edge. So if we map out our adjacency list here, so we have 0, which goes to, let's say a list of tuples, right? And then right now we can see the most direct edges and nodes is 1 and the direction is 1 since it's going towards it. And then we have 4 and 0 since 4 is pointing towards 0. And 0 just means that it's an incoming, where 1 means it's the outgoing. So 1 is outgoing, 0 is incoming. Okay, so then now we consider 1 here, and then we're going to see that it is pointing towards 3, and that is 1, and that's it for that node. Then we're going to look at 2, which is, or we can do it by the depth of it. So we see 3, which has or also we need to consider that there's 0, and then it's an incoming connection, so it's 0, 0, and then there's 3, and then that's a 1 since it's outgoing from 3. Then there's 3, which has 1, 0 since it's an incoming, and then 2, 0. So 3 has 2 incoming connections. Then we have 2, which is just 3, and that's just going to be 1. And then we can do it again for 4. Let's just write out this entire one just so that we have the most clarity out of this. So for 4, it's going to be 0, and that's going to be an outgoing one, so 1. And then there's also going to be 5, which is incoming connection. So that's that's going to be outgoing. So 4 is both outgoing, and it's going to be 1. And then we finally have 5, which just has an incoming connection from 4. So it's going to be 4, so 0, right? Okay, so how do we build this adjacency graph, adjacency list? What's the purpose? What are we going to do with this? So what we're going to do after is we're going to start, since everything needs to connect to 0, like we could just track all of our minimum changes by by first calling like a DFS operation on 0, saying, okay, so start at root 0 and go to the depth of go through like however, like if we see a node here, and if it's not, like we're going to have a visited list so that we don't have any duplicates because we're trying to find the minimum changes. So we're going to go inside of this list if it's not within our visited list, and then we're going to like add however, like, because we know that every time we see a 1, which is an outgoing connection, we know that it always needs to be an incoming connection, because we're starting, when we're building this adjacency graph, we're starting from 0. Everything needs to be pointing back towards 0, and since like 0 is a root node, that means that everything that is just outgoing needs to be it needs to instead be an incoming connection, right? And we want to prevent duplicates as well, since we're trying to find the minimum number of edges changes. So that means that we just we have a visited list so that it prevents us from counting duplicates, and we just go through each node inside of the adjacency list, and then we just keep adding the outgoing connections, because that means that they need to be converted to incoming direction. We don't need to actually flip it and return the graph. We just need to count the minimum number of edges that need to be changed, right? So let's build this adjacency graph out first. So what we're going to do here is we're going to say we're going to have like an adjacency list, which is a default dict of a list, right? And then we're going to say for A, B in connections, which is just going to go through each element in the array, and it's going to give us 0 and 1. It's going to do a decoupling. And then when we have that, we're going to say adjacency of A dot add B, and so let's see, here's adjacency. So if we have 0 here, and then we had like 0, 1, that needs to be B1, and then for B's case, which is just B1. So let's just take this first element as an example. We have A, and then we have 0 here. So we're gonna add B and A, and then we're gonna just return this to see how that looks. Pen or adjacency of A dot add out there. Oops. Yeah. Is it just a pen? Oh wait, that was pretty slow. I already saw that. So yeah, we have 11,040,00,31. That's exactly what we want to see. Now the next thing we want to do is we want to kind of set up our DFS. So we know that we want to return DFS on the city 0. So that means that we have to return some integer outside from the DFS. So it's going to be DFS of city, which is going to be our argument. We're going to have a visit. We're going to keep track of the visitors or the nodes that the cities that we visited. So we have an empty set for now. And the first thing we want to do is we want to set this edges count to be 0, because we're going to start from like, let's say the edges changed. We start from 0. There's gonna be no edges changed, so we're just gonna keep counting down every time we call like another DFS operation on its neighbors. So we're gonna have edges changes be 0. We're gonna add to our visited list the city, and then we're gonna iterate through the adjacency list at this node. So we're gonna say for neighbor and the direction in adjacency at city. We're going to say that if neighbor not been visited, then we're just going to edges changed is going to be equal, and then we'll just return edges changed. Edges changed is going to be plus equal to the direction plus DFS on the neighbor. And that should be the solution. Yeah. So it's pretty straightforward once you get the adjacency list. But the thing to understand here is that when you see a DFS problem, the first thing you need to notice is that it needs to have a visited set. And the second thing you can notice too is that if there is like a direction, like something that has to do like a tree or a direction, and that's important to notice, then we can use an adjacency list so that we can understand the relationships between nodes within this graph. I think that's a pretty important concept to know. I think the adjacency list is probably the most finicky part of this problem, and also understanding that like you can go through the root city, and then when you go through there, like you can count the number of edges changed. You can add it to a visit list to prevent duplicate once again. And we can just iterate through all the neighbors within the adjacency within like this adjacency list, and then we can add it by like the certain direction, because we know that when we have an outgoing like edge, that just means that we need to flip that so that's more it's incoming to this node at least. And yeah, that is how do you solve this problem.